All right, so we're going to study section 5.1, which is our introduction to solving systems of linear equations. And specifically today, we're going to solve them by our method of graphing. So the first part that we're going to start with today is just some background information. So up until now, I'd say we've solved equations that look like this, like -6 is equal to x plus 9. And as I wrote down here, when we're solving an equation like this, we're trying to find the value of the variable. So in this case, our variable is x. That would make the equation true. So we do things like I would subtract 9 from both sides. So -6 minus 9 is -15. The 9s would cancel, and I get x. So we're just trying to find the value of the variable that makes that one equation true. So our answer, as we see on the notes here, is called our solution. And our solution is the solution because if I put it back into the original equation, so if I took the original equation and instead of putting an x, I put what I think the answer is, so -15. So on the left side, that's -6, and -15 plus 9 is also -6. So this was true. So that's why I know that this was my solution. So what we're moving forward to is a system of equations. Now, system in mathematics is just going to say two or more things together. So here's an example. I have two equations, x plus y is equal to 7, and 2x minus 3y is equal to -11. So this is a system of linear equations because there's two equations that we're trying to solve and there's two variables. And another thing that we want to note is that it is linear because both of these are forms of lines, right? We know the forms of our lines. It's important to remember that we have like our standard form, ax plus by is equal to c. So I can see that both of them are in that standard form. So what we're thinking about with a system of linear equations is that when we're solving these, we're trying to find both values of the variables that would make it true at the same time. So like here, we're working on one equation at a time. We're just doing one equation so we can find one variable. What we're thinking about here is if we have two equations, we're trying to find two variables that make it true at the same time. So our definition for the solution then, the way that we'll know that we found an answer is we'll find the values of all the variables, and when I plug them back in to each equation, it makes both of them true, or in other words, all of them true. So let's see what that looks like. So I think that the answer is the ordered pair 2, 5, and I think that is the answer to this system here. So I'm just going to take that system, and on your paper I would just ask you to rewrite that down. Let's take that system, let's put it down here so we know where it is. Now if we think something's a solution, so we think 2, 5 is the solution, that means we think the x value is 2 and we think the y value is 5. So instead of writing it as a separate line, we always put it as an ordered pair. And we'll get to that in just a moment, why we list it as an ordered pair. But it's an easy way to group an information of x and y together. So if it really is a solution, that means I have to plug x and y into both of the original equations. So I'd take this blue one, and instead of x, I would put in a 2. And instead of y, I would put in a 5. I want to make sure that makes that one true. Well, this is true because 2 plus 5 is equal to 7. So it makes the first one true, but it has to make all of them true. So it also has to make the second one true. So I have to take the second one, and instead of x, I'm going to plug in a 2. And then instead of y, I'm going to plug in a 5. And I'm going to hope that equals -11. And we see it does, right? 4 minus 15 is -11. So it made both of the original equations true, or in other words, it made all of the equations in the system true when I plugged it into them individually. So this ordered pair is a solution. Now, today we're going to be focusing on solving a system, like how did I get this answer? How did I get 2 for x and how did I get 5 for y? And there's a bunch of different methods that we have and we're going to study them individually. So today we're just going to be looking at graphing. And that does inform us as to why we usually like to list our answer as an ordered pair. Because when I think of an ordered pair, I think of a position on a graph. So our knowledge for today, when we're solving the systems by graphing, the solution for that system will be where the two lines intersect on a graph. In other words, the point of intersection. So if we look at our example here that's included in our notes, there's two lines. There's this equation, and I know it's a line because it's in slope-intercept form. So it has a negative slope and a y-intercept of 5. So here's that line. And then the other equation in the system, another line because it's in slope-intercept form, is right there. So we'll highlight it. It's in red. And what we can see is that they intersect. Where do they touch? The x value where they meet was 1, and the y value where they meet was 3, which means that is our solution to the system. So again, we can check that. We think that 1, 3 is the solution to the system. So if I plug it into the blue one, so instead of y, I replace it with what I think it is, 3, and then negative 2 times x plus 5. And it does make this one true because 3 is equal to negative 2 plus 5. If I take it and plug it into the second one, again, instead of y, I think that's 3. Does that equal 1 times 4 minus 1? And it does. So we can see that by looking at a graph, if I take this line and the other line and look at their graph and see where they touch, their point of intersection gives me the x value and the y value to make the solution to my system of equations. So our goal, or our method, will be I'll give you a system, something like this. We can see that we have two equations. They're both in slope-intercept form. And since we have two equations and two variables, we know that this is a system of equations, right? System just means we're doing more than one at a time. So this will be our method for how we do it. What we should do is we should graph both of these lines and see where they intersect. So if I take the first one's in slope-intercept form. So its y-intercept is 5, and its slope is negative 1. So we'll start at the y-intercept of 5, and we'll go down 1 over 1. So we'll create this line. Now we're going to plot as many points as necessary, or I should say as possible, so we can have the best line. And then we will connect them to make our line. So that's step 1, graph the first one. Step 2, all right, we're just working on graph each equation in the same coordinate plane. So I graphed the first one, now I'm going to graph the second one. This is also in slope-intercept form. The y-intercept is negative 1, and the slope is 2. So I'd start at negative 1, and I go up 2 and over 1, up 2 and over 1, up 2 and over 1. And I'd keep doing that, and I'd make my line. I could go down 2 and over 1 as well. So when I connect the dots here, I can see that I have a point of intersection, right here. That point is on both of the lines. It's on the red line and it's on the blue line. So I can see where it is. So its coordinates, the x value is 2, the y value was 3. So I think this is our solution. The coordinates of x was 2, the value of y was 3. So then I should check it. If I think 2, 3 is the solution, I should take the blue one, and I should be able to plug in x and y. So I think x was equal to 2, and I think y was equal to 3. So we'd plug in y, and then we'd plug in x, and we do see that that works. 3 is equal to 3. All right, this is the example that we were seeing above here. And if I plug it into the second one, instead of y, I think it's 3. And here again, we do see that 3 is equal to 3. So the way that we got the solution to 3 was we graphed the first one, and we graphed the second one, and we saw where they touched. So we'll do one more example here. And here's the only thing that I want to clarify about how we do it in our class. When we're solving a system by graphing, for my class specifically, I want you to make sure that you are graphing as many points as possible, and that your point of intersection is actually a dot that you placed when you were graphing both lines. So what I mean by that is, like, when I look at the first line here, so again, we're trying to solve this system, and I know it's a system because there's two equations, and I'm trying to find the value for two variables. So this one is in point slope form. So maybe it'll be helpful to rewrite real fast so that it's in the correct form with the minuses. So instead of +1, we could write -1. So I know that the point on this is -1, 3. And my slope is 1/2. So in this form of the line, I already have the slope, so I can place a lot of points on this line. So we'll start at -1, 3, and our slope is 1/2, so up 1 over 2. Now because I have the slope, I can place a lot of dots, which means I have a lot of opportunities to see if there's a point of intersection. But when we look at the second one we'll notice is in standard form. Now, when I think about standard form, I could try to graph it using the x and the y intercepts. So if I think about the x and the y intercepts with this one, the x-intercept is not nice, right? If I let y equal 0, I get -7/3. And then the y-intercept is nice. The y-intercept is just simply -7, right? Just letting x equal 0. But first of all, graphing -7/3 is a little bit difficult. I can place the y-intercept pretty quick, but -7/3, that's -2 1/3. So if I tried to estimate that, it's there, but when I connect the dots, I don't know if that's exactly where it is or not. It looks like it is, but that's what we're getting at with our method of graphing, is rather than trying to estimate, you might want to convert a given equation into a form that allows you to see slope. So for example, I might want to take this and convert it to slope-intercept form. In other words, get y alone. So that would tell me that y is equal to -3x minus 7. If I use that version of it, I can graph the y-intercept at -7. But now I have the slope. If I have the slope, I can put a lot more points on the graph. So then I do see that I've placed a dot twice. And I can see that this point right here is where both of those lines intersect. So its x value was -3 and its y value was 2. So we should check that in both original equations. So if I take the original blue one, y minus the y value, which is, so y is 2, minus 3, because that's the original equation, should equal 1/2 the x value that we think is -3 plus 1. So 2 minus 3, that's -1. -3 plus 1 is -2, and half of -2 is -1. So it made the blue one true, and we can make sure that it makes the red one true as well. For the red one, instead of x, we think our x value is -3, and instead of y, we think our y value is 2. We're hoping that gives us -7, and we do see that it does. -9 plus 2 is equal to -7. So in summary, when we're trying to solve a system by graphing, all we have to do is graph all the equations and see where they touch. Then to check them, we simply plug them back into both originals and make sure that it makes both original equations true.